So, as Laura mentioned, my institute, we work across disciplines and we work on societally relevant problems. And one of the things that work actually does is motivate really interesting climate questions. So I'm a climate scientist. I'm going to be talking just about climate today. You're not going to see anything on agriculture or policy or anything like that. But doing science that can inform those things is certainly very important. And that's a critical role that the universities and research institutes like mine can play. So this really is a new frontier, decadal variability and prediction. Even though people have been working on it for a couple decades, it's still really a frontier. I mean, we were working on seasonal prediction for at least that long before we started doing anything in real time. And this is a much harder problem. So the structure of my talk is given here. I'll provide some background on exactly what it is that I'm talking about with respect to decadal variability and why we should care. I'll provide some background on just the physical processes leading to what we understand in terms of modes of decadal scale variability. This is where we can potentially mine something predictable and then look to experimental decadal predictions. Now, I'll tell you right up front that I think that these have limited value, the decadal predictions so far. This really is something that we're just very much learning about. But you have to go through that exercise of actually making forecasts before you realize where the problems are. And there are a lot of problems here. So the majority of my energy will be spent on that. And then just at the end, a little study that I've done with a colleague of mine recently on looking at interannual variability in these decadal predictions. So starting with background, what is it? Why is this important, and exactly how important is it relative to other things going on in the climate system? So in terms of decadal variability, we use that term very loosely. It really refers to variability, natural variability in the climate system that's happening on time scales typically of 10 years and more.
Hello?
Now is it on? Is it on? No? Yes. Is it easier for me to turn on again? Good. Yeah.
Hello? Okay.
We start all over now.
Okay, so I mean, decadal variability actually encapsulates a lot of things, and you'll see a few of those here. But typically when the climate community is talking about decadal variability and trying to predict decadal variability, they're talking about these long-term fluctuations in the climate system, primarily those fluctuations in the Pacific Ocean, and most of that work has been associated with Pacific Decadal Oscillation, although there's very many names for that same thing. And then in the Atlantic multi-decadal oscillation. And you can see that these are not regular periodic things, for one. Certainly, especially in the Pacific, there's a lot of interannual variability that we're just sort of, by rectification, pulling out these long time scales. But it's not a regular thing, so it's very difficult to say based on where we are now, when we expect things to turn around. And even what's the necessary return period. The other thing is that we have very few realizations of these things, which also adds to the complexity. So the motivation for trying to say something on the decadal scale, for us anyway, was really motivated by the demand for climate change information. And when the IPCC was first put together, what really motivated was being able to answer the question, are humans having a discernible impact on the climate system? And we know that the answer is yes. But the push for information from the IPCC has gone a lot further than that now. People are asking very specific questions. People are probably asking questions that are too specific for that data to handle. But for example, what this is showing on the left is the temperature change in all those IPCC models, expected in this 20-year period, which we're already in, so centered on, say, 2020, the following 20 years, excuse me, these are all that 2011 to 2030, and they're from just different scenarios, and this is from the last IPCC report. And if you're going to say something about the next 20 years, are these climate change simulations the right thing? The other thing that you can see, though, is that at the next 20 years, or part that we're already in, there's very little difference between the different assumptions on how the greenhouse gases are going to change and the regional climate response. So what are the other factors that might influence climate on the next 20 years? This realization that the different scenarios don't matter that much over the next 20 years is a critical piece of the decadal predictions, as we'll see a little bit later. But if you're going to use those IPCC models to say something about the next 10 or 20 years, how do you handle these decadal scale fluctuations in the climate? So even for temperature, and I'm just looking over these subcontinental, pretty large boxes in Africa, and we've filtered out the year-to-year stuff. The black line in these graphs is the observations over the 20th century for temperature, and the colored lines are some collection of the climate change models. And so the climate change models have decadal variability in them. They have those processes, but they're not designed to predict that decadal variability the next 10, 20, 30 years into the future, because that's climate noise into them. And so whether or not you get this peak at the right time could be very important for the purposes you're using these predictions for, with these projections. And then all of these things are being realized at the same time. So really the decadal information that you want is, what are our expectations of the next 10 or 20 years? For the people making decisions or being impacted by the climate, that's all of these things together. It's the decadal variability, whether it's natural or just some smoothing of stochastic noise. That decadal realization over the next 10 or 20 years is important, but that's on top of climate change, and on top of that are the year-to-year fluctuations. So all of those we're going to experience over the next 10 or 20 years, and you want to be able to capture that as much as possible. This is an example of what we call timescale decomposition, and it's using observations just to look at how relatively important were these different timescales over the past. So again, we're using observations from the entire 20th century, and this is for the globally average temperature. The black line at the top are the observations from year to year. And what we've done in the red line was to extract a trend. It's not a linear trend, but if we look at what would we expect for globally average temperature based on how CO2 is changing, for example, we can create this trend line, and we will call it climate change. If we remove that, we can then separate what's left as, quote, natural variability into these decadal timescales in the green, and the year-to-year variability in the blue. And you can see that for the global average, climate change is the biggest part of what we've experienced over the 20th century. It's not necessarily true when you look locally. And even at the global scale, interannual variability, as we know, for example, with El Nino events, has a marked impact on our globally average temperature. But when we're experiencing these slow changes of decadal variability and climate change together, that has an impact on what we call trend, because human memory is just psychology to call what you've been experiencing recently in several years or even a decade as a trend. But if we put these red lines and green lines together, you can see, for example, that in this period here, in the 80s, when I don't have a very steady cursor, when the decadal variability was tending towards warmer conditions, on top of that climate change trend, there was a lot of media and even the scientific community saying climate change is accelerating. During the more recent period, we've heard about a slowdown in global warming, maybe climate change hiatus, all this stuff. We see that climate change is not slowing down, it's not taking a break. But when it's experienced in combination with a cooling phase of decadal variability, the global temperatures warm more slowly. So all of these things come together, and we want to be able to understand and anticipate what's coming in the future. Now I did this for South America as well, just so you could see this comparison. To remind you again that global average, the most important thing was trend for temperature. When you look more locally, that's not the case. There are parts of the world, and this is the color bar that you want to look at down here. There are parts of the world where trend on the left is the most important thing, is the dominant thing that was observed in the 20th century, but there's other parts where it was fairly minor. And decadal variability plays its role, typically 25 to 40% of the variance. In some places, it's the dominant thing. And then the year-to-year variability on top of that. So that's for temperature. Go back to for precipitation, it's a very different picture. The trend has been extremely small for most of the world, just a few percent of what we've experienced. So these maps I'm showing just for South America, but the messages and the numbers for rainfall is pretty consistent worldwide. For decadal, about a third of the variance is in decadal, and majority of what people experience is the year-to-year stiff. And this is really where the shocks come to communities and to economies, ecosystems. So if I were to pick a point near Santiago, pick that grid box, and do that same decomposition of the time series just in that box, this is what it looks like here. And so you can see that even though this time series only goes to 2005, so we're really not capturing this recent period of significant drought in the region, but you can see that there have been periods in the past with prolonged dry periods. And then if you have year-to-year dry events on top of that, that just exacerbates the whole situation. So this is how relatively important decadal variability is worldwide and can be locally. So how can we understand what might be predictable about decadal variability? Again, if you just have stochastic noise in your year-to-year time series, there will be some part of that spectrum that's decadal. It's not necessarily driven by a physical process. But in some parts of the world, it is, and in those parts of the world, it's driven by these decadal modes, quote modes, and that's what we want to try to address in these dynamical predictions of decadal variability. So I will try to go briefly through these. I might have to skip some slides. I told Laura I could speak for half a day. I could give like a whole day seminar. I just love talking about this stuff. Okay. So Pacific decadal variability, how many are familiar already with Pacific decadal or interdecadal variability? A few people. So this work really started focusing on the North Pacific, so I'm going to use that original terminology, which was PDO. But we recognize that there is some symmetry about the equator, and that's led to this interdecadal Pacific, which treats the entire Pacific Ocean. So this is the same time series that I had shown before, where these red areas are indicating the positive phase, and the blue areas are indicating the negative phase. And what's shown in these pictures of phase is, in color, those are the sea surface temperatures. So during the positive phase, it's typically warmer in the tropics and cooler in the mid-latitudes of the Pacific. Overlaid on that are contours of sea level pressure, and you can see the wind vectors that tend to be in that phase. So that's about one, these are in standard deviation, so that's like one standard deviation of this time series. So when the time series looks red and strong, it looks very much like this pattern, and when it's blue and strong, it looks very much like that pattern. And you can see that there's a lot of noise in this. It's very hard to tell even where you are now in the Pacific decadal oscillation, let alone where you're going to be in 5 or 10 years. You'll notice that it's very similar to El Nino in the tropics, and that's for a reason, which I'll come to in just a moment. So the main difference is if we just look at a composite picture of El Nino on the bottom here, most of the signature is in the tropical Pacific. There is some cooler conditions in the extratropics, But when you focus just on the Pacific decadal oscillation, and again, this is the North American focus, you see that the signature is much stronger in the extratropics. And that's again because of the longer time scale that's sort of muted out the variability in the tropics. So what's the mechanism behind that? There's been some really interesting studies. This is one of my favorites by Mike Alexander, where they took some simple models and they tried to understand, because of this symmetry, how the tropics might be driving this mid-latitude variability. And so this is an observational analysis where they look at, if we take this box in the tropical Pacific that's usually used to refer to El Nino, and then do a correlation with all the rest of the ocean temperatures around the world, what does it look like? And so, for example, this is the type of sea surface temperature pattern that you would typically see during a strong El Nino event. Now, if you use that temperature variability in that box and actually drive an ocean model with it, just for the heat and heat fluxes from that, what can you do with a simple ocean model? And the hypothesis behind that, and what they go on to show in the paper, is that the process is what they call an atmospheric bridge. So the driving conditions for changes elsewhere, and this is sort of a teleconnection summary. So you have conditions changing in the tropical Pacific, and the heating of that, kind of like dropping a stone in a pond, except for you're sort of pushing the pond from underneath. So you have the stratified atmosphere, and the heating from El Nino is sort of pushing on the pond from underneath, and is creating these waves that radiate out from the tropics. And so those waves end up influencing even the surface winds and sea level pressure outside of the tropics. And it's those changes then that influence the winds that affect the advection from colder water, that affects the heat fluxes due to increased winds. So this is the idea, that you have this bridge that goes through the atmosphere due to the heating of El Nino. And so the sort of first order hypothesis on what's driving the Pacific decadal oscillation is this atmospheric bridge. We now know that there's a lot of other processes going on as well, and that makes it more complicated. But this is a primary one. Now, how does that, El Nino happens year to year, so how does that actually end up influencing decadal variability? This was a big question, which was answered by Clara Desser a little bit later, or actually a little bit, she was looking more observationally, so, but they've built on Mike's work since then. So what you're looking at in these different graphs is going down in the ocean. At the top is the surface, at the bottom is 400 meters, and those are temperatures, changes in temperatures at those different levels in the ocean. So the idea in this re-emergence theory is that El Nino peaks near the end of the year. In the northern hemisphere, at least, that's the winter time. You have the storm tracks coming through, so you have strong winds, and it's really mixing up the mixed layer, that upper part of the ocean. So if you change the winds and you change the heating, you're able to affect a pretty deep layer of the upper ocean, because it's deep, it's being stirred up by the winds. In the summertime, when it's being more heated from the surface, that disconnects the surface from that deeper condition that you put into the ocean, which can then come out again the next winter when the winds come back and stir it up again. So at the surface, you see much more year-to-year variability. In the deeper depths, you get more persistence in those temperature anomalies. And they've shown this in some models as well. Again, there's a lot of things going on, so it makes it fairly difficult to pull this out of long observational records. But this is an interesting theory on how you get that decadal persistence. So turning to the Atlantic, so the dominant mode in the Atlantic is this Atlantic multi-decadal oscillation. The index for it is much simpler. It's really just looking at the average temperature over the North Atlantic. The time series that you see here has had a lot done to it. So the Atlantic is not as nice and clean as it looks from that time series. You've taken out the year-to-year stuff. You've taken out the trend. You'll see all that mess thrown back in later. But it's a very long time scale. So we really, from the actual measurements, actual temperature measurements, we have very few realizations. But we know from some paleo data, like tree ring reconstructions, that there is a signature of AMO that goes back pretty far, at least several hundred years. And so the top black graph is, and again, this is multi-trended, the top black graph is that same, let's go back, is the same instrumental measurement that I showed earlier, and then the tree ring reconstruction is at the bottom, and you can see in the overlapping period it agrees pretty well. So we believe that Atlantic multi-decadal has been going on for a long time, but what you can see with a longer record is really how irregular that time series is, how many, 20 years to 100 years of length in that variability. So now what causes this? It's very different from the Pacific decadal oscillation, and what's important in the Atlantic long-term variability is the overturning circulation of the ocean. That's density driven here. So what happens is at the very high latitudes, I'll go ahead and put all the words here. At the very high latitudes where you have cold water and you have ice forming, the salt in the water actually makes it lighter. So as the ice forms, excuse me, the salt makes it heavier. So as the ice forms, it leaves more salt behind in the water, and the water becomes very dense. And so that cold, salty water can sink. Anything that happens to make that water lighter or fresher will make it harder to sink. So one idea of this very slow, sluggish overturning is that as you create more dense water, you speed up the sinking of that high latitude water. It's replaced by the water that's moving from the tropics to the high latitudes. So you're speeding up that circulation, but by speeding that up, you're bringing more warm water, lighter water, to the North Atlantic, and potentially making it lighter and harder to sink. That will slow down the transport from the tropics to the high latitudes, which then makes it colder and you start forming more ice. So you can imagine that there's this sort of oscillatory pattern that could happen in making more or less ice and the speed of transport from the warm tropical water to high latitudes. Why should that take 100 years? It's an extremely slow, sluggish process. And there's been other theories on what could additionally enhance that we also see in some of the impacts. And one of those has to do with the intertropical convergence zone. So just to orient you, this the equator, so we're looking from north to south. The equator is here. So we have the intertropical convergence zone. That's this very strong band of rainfall near the equator, but it always stays north of the equator. And so when you have a strong overturning circulation, and this is meridional overturning circulation, so when you have a strong overturning circulation, and that's bringing a lot of that warm tropical water poleward, then that warm water is feeding a stronger convergence zone and shifting it farther north. So that's making the water not only warmer, more warm water, but also fresher water. So that's a theory that's contributing to it. And as that water gets fresher and lighter as it goes to high latitudes, again, that slows down the sinking and you switch into the reverse. So there's a few theories on this. The impacts of having a warmer North Atlantic are quite varied. They actually have been documented to extend as far as India. This is the real time series with the noise and the trend all in there. But in particular, it's been linked to drought in the US. It's been linked to stronger hurricanes over the US. You have that warmer water, more active convection. As it pulls the ITCZ north, that leads to more rainfall over the Sahel. So there's a lot of reasons why, especially in some of these vulnerable areas of the tropics, we would want to be able to predict this. The Europeans are very interested in predicting this because it does affect their winters as well, and the Europeans have very little to go on in terms of prediction, so anything that they can mine from the Atlantic would be good. To show you an example of West Africa, so here's another one of those decompositions. Map is showing you the decadal variability importance. So just focusing on this area of the Sahel, this is a somewhat unusual picture for prediction in that the components are quite large across. So this is one of the parts of the world that has a pretty large trend in rainfall. This is one of the largest trends anywhere, 12% of what they've experienced. 40% of the variability is in decadal, and again, we believe that's due to this Atlantic overturning circulation. And having these dry periods punctuated with dry years are the most devastating, and there are plenty of humanitarian reports that document what's happened in those years. Okay, so the U.S. What they've done here is the U.S., as you can visualize, is between the Pacific and the Atlantic, so we're impacted by both of these things. There was a study done based on observations that looked at the possible matrix. So when the Pacific is in its positive phase or when it's in its negative phase, similarly when the Atlantic is in its positive phase or negative phase, how do those things interact over the past? And looking at the change of drought frequency. So where you see red colors, those are where droughts are more frequent in that configuration, and where it's blue colors, that's where wet conditions are more frequent in that configuration. And what we've been experiencing lately, like since the late 90s, was a negative PDO and a positive AMO. That's this one down here in the bottom corner. Obviously quite bad for California in the south, and that's actually very much what we've been experiencing. I'm not going to go through more details. So on the experimental predictions, again, this design came out of the IPCC in the interest to provide more useful information on the 10 to 20 year time scale, and that's led to a coordinated set of experiments that's been really valuable for our research. And also show you some initial papers from really pioneers of that effort, and then some work that we've done to represent skill in that. So the motivation, again, going back to this, the overturning circulation and the AMO, really the focus, because we realize that the Pacific decadal oscillation is very messy, it's very hard to predict. The focus has really been on, can we predict the AMO? And also because the Europeans have a lot of money to study this, so there's really been a lot of focus on the AMO. And the idea was they knew from their models, these figures on the left, that when the AMO was in its positive phase, the sea surface temperatures look like this. That looks like what we observe as the AMO. So, excuse me, this is the model, this is the observation. So their model does the same thing. When their model has an active overturning circulation, it has a pattern that looks like the observed AMO. So the intention was, if we can get the model to produce this variability in the overturning circulation, then we can reproduce the AMO, and if we can predict those changes in the overturning circulation, then we can predict the AMO. So the model simulates it, just doing its own thing. How do you get it to predict that? Well, what you need is the ocean conditions. And we're going to get to that in just a moment. First, here's the experimental design. So this was the coordinated experiment for the IPCC, and this is what they call a donut diagram. But all the work happens in the hole. So it's the pink stuff in the middle that everybody had to run with their models in order to contribute to this collection of model hindcasts. So the idea nominally is to, you start your model near the end of the year, or December, January, you start your model, and then you run it forward for 10 years. And then 5 years later, you start your model again, you run it for 10 years. You keep doing that. And the reason they were doing these every 5-year starts, because that's a lot of data to run, and it was very hard to get a lot of model groups to participate without those fairly relaxed requirements. Thankfully, there were a number of groups that started their model every single year, because those are the experiments that have proved to actually be useful. Okay, so that's the experimental design, and the difference between this and the regular climate change projections is just to start the ocean out with observed conditions to the extent possible. So they're the same models, they have the same assumptions on increasing greenhouse gases. You're just trying to start the ocean state out close to observations so that the intention is that inertia in the overturning circulation carries forward for the next 5–10 years. That's what they're hoping to see. So where do we get that ocean data? The primary source are in these Argo profiling floats. And what these floats do is they are at the surface and they go down 2,000 meters, they drift around, and they pop back up again. And each time they go up and down, they measure that whole depth of temperature and salinity. So you can create these density profiles around the ocean and use that, assimilate that into your ocean model, and that becomes your initial state. Where are those floats? They just started deploying them in the early 2000s. So in 2004, this is what the network looked like. In 2015, it looks like this. The dots got bigger. So it looks like the ocean is really covered. But even these dots here, this dot is it's probably about the size of Santiago. Those floats are about the size of a man's leg. So the ocean is really not very well covered. But I will note, there's no floats from Chile. Come on, you guys. I mean, I looked, so Bolivia doesn't have one, so okay. But Gabon has one, and Bulgaria has 3, so come on. I think Chile needs some floats out there. These are really important for that initial ocean conditions. Okay, so these are the pioneers. There are 2 papers that came out pretty close to each other. The top one is from Doug Smith at the Met Office, UK Met Office, in 2007, and then closely followed by Noel Keenley's side from Max Planck. Yeah, I have definite opinions on these papers, as you're about to hear. It's a tough thing because it's in early days, right? You're talking about something that nobody's really done before. But I think this is a really important lesson for all you early career scientists out there, maybe even, the rest of us. How to write a responsible paper. For those of you who want an example of the opposite, I highly recommend reading the Keenley side paper. I know Noel, so in case you're watching this, Noel, I love you, you're a great guy. He's a very good scientist. I think he just kind of became the fall guy for this publicity stunt. But, okay, you'll get more commentary as we go. So these were the claims that were made in the abstracts of those papers. I'll let you look through those. Doug Smith at the top, indicating creating information on both the internal and the externals for climate change and the variability, both globally and in many regions. The Keenley side paper makes much more definite claims. The overturning circulation will weaken to its long-term mean, so that these natural climate variations will temporarily offset the projected anthropogenic warming. Now, when this paper came out, I don't know if you guys know realclimate.org. If you don't, it's a great source of information. They were very upset by this paper. And they made a bet with these guys in 2008. We bet that the globally average temperatures are going to go up over the next 10 years. And they bet them like 100 pounds or something. And they did not take the bet, which is good because they would have lost. The temperature has been going up, in fact. Okay, so let's look at how that's presented. And I think, well, the reason that I included this is because there's so many ways to present these predictions. And I don't know if anyone's really figured out the best way, and probably the best way differs depending on who you're talking to and what questions they're asking. But there are a number of ways of presenting that. So in each case of these graphs, the red information is from the model, and the black line is from the observations. So the top graph is showing what did the predictions say for that next year. We initially, it's a forecast, we run it out 10 years, but just that first year of the forecast, what does it say? And so you can compare the model with the observations. You can see they're really just starting here in the early 80s. Most of what you're seeing is volcanoes and El Nino. Right? That's mostly year-to-year variability that you see in that first year. The center graph is if you took the 9th year of the forecast. So it's still 1 year, but it's 9 years out from when you started the model. And one thing that you see is how much the uncertainty has changed across the ensemble members. I think that's a really important message. You're still seeing the same observations to the extent that you can, so you're still seeing this primarily year-to-year variability, the volcanoes and the El Nino. The bottom graph is if you took that year 2 to year 9 average, so you're looking at a very long time average in both the observations and the model, so it looks primarily like trend. You're not seeing, this is globally average, but you're not seeing a lot. What you do see in the model here and a little bit in the observations is the response to the volcano. Not too low. So here's the Keenly side projection. Again, I'm going to refer you to look at this in more detail. It's really just the graphic showing that they believe their prediction, which, let me see, the prediction is in the green, is going to be cooler over the next 10 years. I actually don't even see that in their result, but that was the claim. Here's some skill information that they show from their paper, which I also find is interesting. This top graph is a difference in error. So error is bad. You want to reduce your error if you're doing something useful in your forecast. So it's a difference in error between predicting with initial conditions and just projecting using greenhouse gases. So you want the colors to be blue. You want the error to be smaller in your prediction. The worst error by far is in the North Atlantic, which is exactly what they're trying to predict. And then they have this verification that I also don't understand on the overturning circulation. Now we don't have observations of that going back to the 50s, so that's kind of questionable as well. All right, that's enough giving those guys a hard time. Okay, so there was an activity that was organized by Clivar to look at all of these models that have done these hindcasts, starting in 1960. And we looked at that with a particular question in mind. The question was, is that initialization leading to better information than if you just had the climate change projection? Now, if you're going to use the information, you really just want to know how good is the information over the next 10 years. But if you're going to spend all of that effort, and there's been a tremendous amount of effort and investment, I still think worthwhile, but tremendous amount of effort to initialize these predictions and run them and look at them, you want to show that you're adding some value. So all of these graphics are showing the difference between the predictions and the projections. So the main score we were looking at was the mean squared skill score, which is a measure of accuracy. But an important component of that is correlation. Temperature is at the top and rainfall is at the bottom. And so we see that in terms of accuracy, the initialization actually does improve things quite a bit. And this is the 10-year average. This is year 2 to 9. So the initialization does help, for sure. But it does not improve the correlation in very many places. So what that means is that you're not getting the model going up and down in the decadal time scale. You're not getting it to go up and down the same as the observations, but you are reducing the error, and we believe that's because you're just starting the model off at a better place. So if your model, say, has too strong or too weak of a trend, it will have drifted off from observations by the time you initialize, even over a 10-year period. So just by pulling the model back to a more accurate starting point means that at the end of that forecast, you're still closer than you were, even if you're not getting the ups and downs. So that's an improvement. For rainfall, which is at the bottom, we see very little. It's very noisy. And I do have some examples from individual models. I'll just show you one to show you what we're looking at. So for example, this is for temperature from the GFDL hindcasts. And these are the ones that look all red are the ones that are actually that accuracy measure from the model itself. So from the prediction in the middle and from the climate change projection on the bottom, and then the top is the difference. So this is just one model, and with the every 5-year starts. So that's that accuracy measure, which is a combination of correlation, shown here, and this conditional bias, which is another measure I'm not going to go into detail with. So the correlation, and this is what you'll see in a lot of papers, the correlation of just the hindcasts looks brilliant. Like I have 0.9 skill everywhere. Well, pretty much, not for the PDF. But you had that already for the climate change projection because most of that information was trend. So you already had that skill in there. Why go through all the added effort? And again, I think the reason to go through that added effort is we've learned a lot about the variability, we've learned a lot about what the models can and can't do, and we've thought a lot about the problem. And I think things are incrementally getting better. It takes some time. Okay, I've got a ton of this stuff, which I'm not going to go through. I'm happy to leave the presentation for anybody who wants it. But I will come to this, again, more of a summary statistic of these hindcasts to make the point of the every year starts. So these are just the correlation maps for temperature, and the same collection of models. But this one on the right is ones with every 5-year starts, and you can see just how much noisier the fields are versus the start every single year. The heavy contours are where it's statistically significant. So not only do you end up with a more coherent field of skill that you can assess, but more of it's statistically significant. So you're just reducing a lot of the sampling error. And the same thing for precipitation. We're still not getting a whole lot of information out of the collection of models, a whole lot of additional information. But we have more coherent patterns of skill. And I think some of these regions that we might be able to, because of theory and observations, tie their variability into those large-scale modes are worth investigating further. So this is the type of thing that can be used to sort of provide kind of a guidance, a spotlight for where you might want to look more. Okay, so the last thing I wanted to just introduce quickly was what can we say about other things? What can we say about El Nino variability? Most of the work on looking at the time horizon, how far out can you predict El Nino, has been done using El Nino prediction models. And so statistical models have been run out 1, maybe 2 years, and so some work that Mark Kane and Doc Chen did some time ago showed that for really big El Nino events, you might be able to predict them 18 months, 2 years ahead of time. This gave us an opportunity to look at over 10 years, what can we say about El Nino? Again, because if we can say something about the Pacific, that would be great, and it didn't look very encouraging so far. What we found was actually that we have 3 to 4 years time horizon of predicting ENSO, at least ENSO yes or no. So let me walk you through this graph a little bit, because I know not a lot of people are used to using ROC scores. Actually, it stands for relative operating characteristics, but what it actually comes down to is a matter of discrimination. Does your forecast system say more often the right thing versus just tossing a coin? So if you have a skill of 0, that means that your model can't distinguish between hits and misses. It's fairly random in its ability to predict something. If you have a positive score, the more positive it is, the better. A score of 1 means that you, when there is an event, you've predicted it. When you predict an event, there is an event, and you never get it wrong. That's a 1. That's pretty hard to hit. We're starting out pretty close to that because we have a short lead in these forecasts. So these are our forecast lead years going out here. Again, those are starting near the end of the year, so 1 year out is really 1 year out from the initial conditions. And what this suggests is that the top La Nina events we're able to predict to about about 3 or 4 years out, better than just guessing, and El Nino events maybe 2 or 3 years. All of the little gray lines are the different models, about 9 models that went in here that had every year charts. So that's how the individual models would do. And we further broke it down between making a multi-model ensemble of all of those 9 versus throwing out the ones that we knew were a little problematic. Because this is another thing that comes up a lot, like how many models of the multi-model should we actually include? So we do find that if we really just keep the ones that are credible, we do even better. So this is encouraging. We still don't know what the processes are that are leading to this potential long lead predictability, but I think it's a really interesting question. We've also found then that the teleconnections, the global response to those El Nino events is also maintained out to about 2 or 3 years. The left is the observations. This is the best single model, and then on the right are the best multi-models going down years 0, year 1, year 2, year 3, where the hatched areas are where the models are agreeing in the sign of their composites. So that's potentially encouraging. Of course, it's a little bit less skillful for rainfall, but it does give us some hope. So in summary, I really have focused on decadal variability of predictions, so primarily through the observations and the models. I think that there are other ways, other skills and techniques that can be brought to this problem. It's a really big topic, and so many people are doing really interesting things on it. But in terms of decadal variability, again, that can mean a lot of things. Typically, we're talking about the natural modes of variability, but if you're providing information to a decision maker, policy maker, they care about what's going to happen over the next 10 or 20 years, no matter where that's coming from. The predictions are very experimental. There's so much work to be done there. How do we evaluate them? How do we use them? We went through a lot of these same learning pains with seasonal predictions, and I think that we can apply some of those similar lessons to decadal. And to just really hammer in the issue of skill, it's got its own summary point. So I've shown you the accuracy and the correlation. The reason those aren't the same thing is because we have bias in these models. And it's not just removing the difference in seasonal cycle. We have response bias in these models. That bias might be changing over time because of trend. And it sounds like a very simple thing, but there's been some pretty sophisticated research done just in handling bias. So it's just something to keep in mind and to ask questions about when you're using that information or working on it yourself. So I'm going to stop there and maybe take a couple questions.